All right, thank you. Good evening. Okay, I have a question for you, and I want you to think about this. Why has it been so long for GPS meteorology to take off in the deep tropics? Okay, PWV is the critical value or a critical value. It's very high frequency. It's all weather. It's a mystery as to why. Okay. Now, deep convection and water vapor are intricately related. They dominate the climate and the weather of the deep tropics. So it's, again, a subject that you want to, very different from what we're seeing here, which is based on fronts, temperature gradients. That does not exist in the deep tropics. It's been long known from theory and from observations, always done over the ocean, actually. You can see from these different examples here that there's a very strong relationship between PWV and convection. The one on the left should interest the earthquake types, self-organized criticality. Logistics are a problem. Could that be the explanation? Not a lot of good sites to put a GPS in the middle of the Amazon, maybe on top of the cows there in the water. There's me collecting data in my canoe. So that could be. All right, this is when all the geodesists will leave the room. Can you stick it on a shaky tower that's going like this? Is this really a good idea? Well, we did a paper on this and took a look at it. Can you get good water vapor from a 55-meter flux tower? So we made a little instrument that oscillated at a known frequency and amplitude. We hooked it next to our actually permanent real-time, on the equator, real-time GPS. It was processed by NOAA. We had it there for 4 years. Took a look at it. Let's see. Okay, stationary period at the beginning there, and then the oscillating period. Not a big difference, actually very little difference. The noise was actually attributed to going from gamut to gypsy in looking at the two different, it was Topcon and Trimble. That was where most of the error was. So then what we did, all right, we stuck one permanently. We used UNAVCO's recommended rotten wood chicken coop monumentation. The palafitas, I don't know how you say it in English, yearly flooding, and somebody's backyard in Belém. Okay, first results, this is related to the self-organized criticality. 3 years of data from our IMPA station. Okay, it also supports over-continence, the idea that, okay, precipitable water vapor behaves very closely related to precipitation, all right? What's really interesting about GPS, and this is where we've done kind of some new stuff, is looking at the time evolution. Water vapor conservation equation makes some simplifications, and you basically get the time rate of change of PWV. What we measure with GPS is proportional to water vapor convergence, which is convection. Here's an example. INSAR people, pay attention to this one. The green line is water vapor, PWV. The red line is cloud top temperature. Think of your corrections that you have to make over volcanoes. Use GOES IR. I mentioned that the other day. So we made networks. This was to look at spatial variability in PWV. Also, for the guys that do ionosphere, think about this is on the equator, basically, so there might be some interesting things to look at for you guys. Okay, so we've done spatial decorrelation, spatial temporal decorrelations. You can see on the left, 5 hours before convection, homogeneous, highly correlated. As you get towards the convective event, it begins to decorrelate. It's an interesting scientific idea. It's also a very good metric for models to try to replicate. Okay, you can look at water vapor advection, take 2 sites, watch it go across. You can see it doing it here. Changes once you get precipitation, water vapor falling out of the atmosphere. But again, it's an interesting thing to look at for different reasons. Okay. We went through and we made a bunch of different other networks I'll talk about real quick here. The sea breeze regime in Belém, we did it with the GPM Chuva experiment. GPM is the satellite system that replaced TRIM, if you're familiar with precipitation satellites. We've done more recently in northwest Mexico. Here it's interesting because you have, unlike the Amazon, you have very, very complex terrain, and that affects convective initiation, convective intensification, and propagation. Then we finally did another experiment just this last summer where we brought in the surface. There's water evaporating from the surface. How much does that contribute to the column? We have our GPS, same region, northwest Mexico, southwest US. Can we say something about the hydrological cycle and water vapor transport? Okay, so our basic things that we've been looking at the last few years, look at the very high frequency and spatial variability of water vapor, a closure, so to speak, of water vapor advection. More importantly, data assimilation, that's the new one we're working on. And we've got a project, OTREC, that's been funded. Training, students, this was very nice in Brazil. Ludmila and Glauber are now professors at the Universidade Federal do Pará. My student Lourdes in Mexico knows how to do gypsy. Okay. These guys on the left here, they're kind of the responsible for me, these kind of mafioso guys with the dark glasses. They got me into the GPS. St. Chuck helped me a lot with GPS, thank you. UNAVCO supported all my crazy ideas, and a final to Jim, and also to Bob Nolting, who unfortunately passed away this last year.